Welcome to a new set of videos that I'm going to play with. I'm interested in learning about Rust, and so I'm going to just capture how I figure out how Rust works and what are the cool things about Rust. This is the first one, and so we're just going to do the basics. I'm going to start by setting up my development environment. I'm using RustRover because I use the IntelliJ tools for other things. I did check RustRover has a place where I can do the command line parts of Rust. So I think we'll be fine here. I'm going to create a new project, and I want to call it, we're going to do Hello World, because you know that's what you do when you're starting. It doesn't have the tools, so I'm going to click the download Rust Up. Rust Up is the tool set. Okay, that should work. I'm not sure why that is not. But let's be brave and do it ourselves. When all else fails, do it yourself. Proceed with standard installation. Thank you very much. Rust has been installed. Okay. Cargo has been directory.cargo.bin. Okay. Let's see if we can find. Oh. Okay. Found the standard library. Everything looks good, but I want an application because I'm creating Hello World. Okay, it looks like I wish that I didn't have to do that every time. It looks like you need fn to make a function, a main is a runnable, print line is how you get stuff out. There's an exclamation point on print line, not print line. I'm gonna let that go. I'm hoping something will explain that in a minute. And it should be that I can run this. Okay, my development environment is all set up. I can see that it built it and ran it. Good. Then before I started this, I looked for, because I am a developer who has done things in a bazillion languages, I really don't want the like basic introduction. So I found this gentle introduction to Rust, and it looks like I can wander through it pretty easily, and it's got a lot of examples. So I'm going to mostly be looking at examples and not so much at the English. So there's my Hello World, which is what RustRover gave me, which is good. I can see it. Do they have an explanation about? Yes. So the exclamation mark indicates that this is a macro call. Oh, great. So I need to remember it's a macro to use it. He says just exactly that. Oh, he claims it'll be really smart if I don't put that there. Oh, well, we're gonna need to make it so. Couldn't find print line within this scope. Okay. Add the missing exclamation. Okay. Next code is a variable. Let declares a variable. And I guess I don't have to give it a type. I guess it infers the type. Okay. And printing it out, I guess whatever's here goes inside the curly brackets. Okay. Yeah, print line takes a format string. Very similar formatting using Python 3. Well, if I had coded in Python 3, that would mean something to me, but I'm sure we can figure it out. So let's open up a notepad and keep track of things we might be interested in looking at later. Format strings. Maybe we care about that later. I don't do a lot of C programming that requires formatted output. So I'm not sure that I'll be interested enough to pursue that one yet, but it's a good thing to remember. Another useful macro is assert equals. It will panic. Oh, okay. So this is like assert in C or Java that I can put a check in there to make sure that everything works. Okay. Looping and ifing. There's a for loop for 0 to 5. Not inclusive. That's weird. Why would you make it not inclusive? I guess, well, yeah, when arrays start at 0. But I bet that's a thing that catches people in bugs all the time. Do things conditionally. If yada yada yada, that looks right. There are no parentheses. No, he says there are no brackets around the condition. There are no parentheses around the condition, just like there were no parentheses in the for statement. Okay. Ooh, but you must use curly brackets around the block. I like that. Let's do the same in a more interesting way. Let even odd equal the if statement. Okay, so that's sort of like the ternary if, kinda? In Rust, nearly everything has a value and can be an expression. Well, that's like C. C is that. Almost everything has a value and can be an expression in C. Okay. Oh. Okay. You, the seriously ugly ternary operator, you've just written it out better. Like their syntax is better, but you've essentially made the ternary operator there. Notice there aren't semicolons in those blocks. Oh, interesting. There's not a semicolon. These are not statements in the if and the else. They are expressions in the if and the else. And that's why if I think of them as expressions, then I don't want them to have a semicolon. Oh, that's interesting. Okay, so inside the if, I can put an expression, and then the whole if evaluates to the value of that expression. Okay. Okay. All right, so now let's do a loop and add things up. Okay, so they create a variable and add them all together and print them out. But it fails to compile. Reassignment of immutable. Oh no, are variables immutable in Rust? Oh, I hope they're not all immutable because that's hard. Reassignment of immutable variable. A variable cannot variable. Let variables by default can only be assigned a value when they're declared. Adding the magic word mutable makes it mutable. Oh, okay. Now this is very cool. There's a lot of safety in having variables that are immutable. And so being able to have an immutable variable is a really, really, really good thing. Languages that only use immutable variables you have to use streams or recursion or things to like rebuild it, recalculate, not store it in a different place every time. And my old brain does not think that way. And so those languages are very hard for me. I really like that I can mark a variable as mutable and use it as mutable, but the default is that it's immutable. So that means that things will be safe until I choose to make them a little less safe by making them mutable. That is a slick addition to a language. Rust is both statically typed and strong type. Think of C statically but weakly typed. Yeah, C statically, you have to give it a type when it's declared. But weakly because the machine will convert things between types for you. Python is dynamically but strongly typed. Okay. So statically and strongly typed, that could be very, very cool. I have to think about that. No, I have to watch for that. I like it. I have to watch for that. It does. So I didn't give it a type, even though it's statically typed. We didn't give some a type or I a type up here. So it is inferring the type, even though it's statically typed. So the type is being given by the compiler. I didn't have to say int. It inferred the int from the first thing that we gave it to. That's okay. And comes up with I32. Ooh, a 32-bit integer. So we get to specify exactly how we're storing it. So one of the things that I don't like about C is I say it's an int. And on most machines, an int is an int. But on some machines, they have different byte lengths. And so when you take something in C from one machine and put it on another machine and compile it for another machine, there's a chance that the int will be of different length. I really like that it's making the type be I32, so it's a 32-bit integer. So then it says, if we change that 0 to a 0.0, let's put this in our main and watch what he's talking about. So instead of hello world, I'm gonna do that. Okay, so RustRover is showing us the inferred types, which I like. And I like that it put this less than here. Remember I was complaining about when it said at the loop, I goes from 0 to 4. RustRover has inserted a little less than there to remind me of that. I really like that. I don't know why sum is underlined. I guess that's showing you the declaration of it if you want to. I don't know why I is not underlined. So I'm not sure why RustRover is underlying sum. So before we mess it up, let's make sure this works. The sum is 10. That is correct. So then he was saying, if I change this to be 0, 0.0, then you can see it changes the type that it's inferring for sum to be, I assume, floating point 64. Then the plus equal no longer works. Binary assignment operation plus equals cannot be applied to type F64. So it's not doing any type conversion there. Like, it could pretend that sum was an int. It could add an int to a real and get a real, but it's not allowing us to do that. That plus equals operator is requiring that both sides of it be an integer. Let's see if that's what the explanation they give. Go back down here. Each operator corresponds to a trait. What is a trait? An abstract interface that must be implemented for each concrete type. Okay, so it's like a behavior that goes with a concrete type. We'll deal with traits later. Oh, good. Let's remember we need to deal with traits later. But basically, the add assign is the name of the trait, and it's requiring that everything be integers. I like this not silently converting an integer into a float for you. I think that's really nice. So what it's saying is when we add this integer to that float, we'd have to be explicit about adding an integer to a float. We have to cast that value to floating point explicitly. Oh, so this is how we typecast. So how does that fix it? does that make the plus equal? Ah, yes, it makes the plus equal be able to use floating point 64. So that's actually casting the I to be a floating point 64 instead of an integer 32, and then adding that floating point 64 to the sum using the plus equal for floating point numbers, not the plus equal for integers. Okay. I'm going to have to remember that that's how you typecast. All right, so now we get to do function types are explicit. All right, we're going to put this in and go play with it before we read any more about it. There it is. Does it run? Yes, it does. The square of 2 is 4. All right, so as I read this, I would say this is the parameter 2 square, and they're putting the type after instead of the type before, which is kind of fascinating. Like 30 years ago when I coded in Noop, which is a variation of Algol, that was the way you did types. I wonder why they chose to put the syntax back to the old syntax. Anyway, you pass in a 64-bit floating point number, and it looks like the rocket operator, it gives you the return type as well. And we return x times x. And I pass in a real number into it, and that gives me a result. And I can print out the result. So if we're playing with this is the rules about type conversion, does that mean I cannot pass the integer 2 into this? Yes, it does not. So it's really, really, really not helping me with type conversion. It's making me make those type conversions explicit. Can I do F64? I can, but it gives me a warning. Can replace with a literal suffix? Ooh. The thing that's cool about 2F64 instead of 2.0 is 2.0, it's inferring the F64. If I say, oh, can I say 2.0 F64? Okay, I really like that. The type, when I have a literal constant, I can be specific about exactly which way. If I make it an F32, assuming that's a thing, why can I not? Maybe F32 is not a thing. Is F128 a thing? Valid suffix F. Didn't I just do F32 and it complained? Oh, you know why it complained? Because it's getting passed into an F64. And I said it's an F32. If I said this was an F32, and I said this was an F32, then everything would be done in 32 bits. Okay. So it's being really, really, really pedantic about the primitive, the types, that I have to be very specific to say the right thing. And I guess 2.0, it'll default to F64. But I really liked when I had to say F64. Okay, so why is the return statement grayed out? Unnecessary return statement. Replace with XX. Oh, so I don't have to have the return statement. This is probably like, I think it's Python, that a function will evaluate, no, MATLAB. A function will evaluate to the value of the last thing it calculated, the last expression in it. So, if I did other things before this, let's let mute be equal, and then P equals P times 2. Yeah, all of those things don't change anything. It's still this last x times x is what square is going to evaluate to. So I don't need the return statement. I also noticed that as it took away that return statement, it took away the semicolon. And I think that's because my guess would be I need a semicolon on statements, but I don't need a semicolon if it's just an expression. I'm going to stick a pin in that. The question is, well, the question that we could think about is, when do you need the semicolon? My guess is it's expression versus statement. That would go back. Remember they said in the if thing, don't put the, where did the if thing go? Scroll better. Here we go. This if thing, and he said don't put the semicolons in the box. That was because this is an expression and this is an expression. They are not statements. This semicolon is for the statement. Okay, we're going to go with, at this point, with what I know about Rust, that would be when do you need the semicolon and when do you don't. Okay, so I think I'm finished playing with this. Let's go see where we were. We were down here in functions. Types are explicit. Oh, it knows that it's alcohol-derived languages for those types. There are no integer to float conversions. Yeah, we played with that. And you don't need the return statement. Okay. Oh, they're saying I'm going to get this weird, if I put a semicolon here, expected F64 but found parentheses. Parentheses type is the empty type, not a void, zilch, nothing. Okay. Everything has a value, but sometimes the value is just nothing. Okay, I think this is that there is no ending expression because we've turned that into a statement. And so now it's mad that it doesn't know what to return. And that's why the zilch, nil, whatever those parentheses are called, empty parentheses are called, because there's no expression at the end of this, it doesn't know what to return. That lets it find its F64. Okay. A few more example of this no return. Absolute, clamp. Okay. I'm not going to get distracted by doing things recursively. Okay, those are good. Values can also be passed by reference. Reference is creating by ampersand and dereference. Oh, we've gone back to C. A reference is created by ampersand and dereference by asterisk. So we're going to go play with this, of course. By reference. Okay, so this is using that no return thing. And so this is saying it's going to chase X, dereference X, add 1 to whatever value it got and return it. So if I is 10, I can pass 10 in using the ampersand, and result 1 should end up being 11. I can I can by reference a constant. That's kind of magical. So it's not really the address of operator because the 41 isn't like at a place I can address it. So it's not really the address of operator the way it is in C. It's a reference to it. Okay. We'll think of it more like a reference. Okay. I wonder if like this feels like frightening to me, because if I pass the address of 41, could somebody change the value of 41? But I wonder if this is, remember the let versus let mutable? I wonder if by default parameters are not mutable. And so I can pass in a reference to something and nobody could screw it up. When I run this, do I get 42 like I should? Yeah. Can I say at x equals 42? No. So I can't chase that and change its value. Immutable borrowed content. Okay, so it must, if parameters by default are not mutable, that is slick and safe, because I like that parameters are not mutable by default. Okay, what does he say about that? What if you want to modify one of its arguments? I'm going to add this function here so that I can compare them. Okay, so can I say modifies? Oh, it's immutable. Okay, it's immutable 64. So let's just add something else. Can I say modifies? Oh, let's make an F64. Let F64, no, let real F64 equal 1. Sure, you could do that. And then can I say modifies real? So the difference, when I said modifies, I had to put the mute after the reference designator. And I have to put, I'm trying to say the address of, and it's saying mute. And now I bet it's mad because my let is not mutable. My real is not mutable. Okay. So, I better make this be something other than 1, because I already set it to 1. Ooh, and now we can see I can print multiple things using these little curly bracket things. Did real become 42? It did. If I make it, well, how does that change the output? Perfect. Okay, so I bet that mutability is what saves me from not being able to do modifies on a constant, on a literal, I should say. Yeah, it says no, you can't do that. Not mutable. Okay, so if I want a function to be able to change the value of something, I need to be able to say mutable in it. Can I do that for just a plain integer? Function plain x that is a mutable. That is a mutable integer. No. Oh, but maybe it's confused because it doesn't have a. Oh, to modify it, it would have to be a reference as well. So you would have to do it this way. Okay, I can see that, because we would need to admit that we're passing a reference to the variable in order for the variable that's down here to be mutable, to be changed. So you would have to have the ampersand. And if I did this, then and then I have to admit that I'm chasing it. So mutable parameters are kind of a pain in the neck, which is okay, because most of the time call by value is good enough. Call by reference and then mutable call by reference is different. So it's interesting that there are three types. There's call by value, call by reference, and call by mutable reference. Interesting. Okay, I sort of like that the default is call by value, and that call by reference. Why would I want to use call by reference if it's not mutable? Like, why would you ever do this? Why wouldn't you just pass in X instead of a reference to X? I'm not really sure why you would ever do call by reference. Unless you have things in multiple threads and the value could change while you're here, and you could like wait for the value to change while you're here. Until we get to talking about threads, I don't think you would ever do this. I think if you were doing call by reference, it's because you're expecting to change the value. And so if you're doing call by reference, I think you would do call by mutable reference. Call by immutable reference means that there's somebody else who might change the value while you're in here. And I don't want to deal with that until we understand how threads and things work in Rust. So I think if we need call by reference, we'll always do call by mutable reference. And my C background says a lot of times I need the call by reference, call by mutable reference, because I need to be able to pass back more than one thing. So I'm curious. I'm curious about how we pass back more than one thing. And C, a lot of times you pass back a true or false for where you're successful. And then the values that you found, you pass back in call by reference parameters. This seems a little cumbersome for that, but okay, it'll be fine. It'll be fine. Let's keep playing here. Then throw in the mute because it's not okay. It's explicitly making this hard. Rust has a powerful way to express things like operation proceeded and here's the result. Passing by reference is important when we have a large object and don't wish to copy. That's why you would use pass by reference, the immutable type, because you don't want to copy the whole thing. Like say I'm like passing in an array or something bigger, whatever are the bigger things in Rust, which we haven't figured out yet. But when you're passing in a bigger thing, you wouldn't want to copy the whole thing, and a pass by value would copy the whole thing. Okay. Learning where to find the Rust up doc. Okay, so if we wanted to see the actual documentation, I could do that. Oh, and here is the standard library. So standard library is usually like where all of the types Yeah, okay, so here are all of the primitive types. Tuple. Ooh. Reference. Raw unsafe pointers. Let's try not to use raw unsafe pointers. That's gross. I mean, that would be C. Welcome to C. Modules, I guess those would be sort of like the pound include things. Macros, that's where we got the printf. Oh, there aren't really that many of them. When there was that, remember the exclamation point? There aren't that many of them that you'd have to do the exclamation point. Async, wait, loop, okay. Okay, so we need something about dealing with futures, and here's traits and things. Let's put over here. We want to remember futures. Organize code into modules. Okay, so that gave us the documentation. And then we're starting to do like other stuff. Arrays and slices. I don't want to go to arrays and slices. Now, the only thing is, at this moment, I have like the basics of how I would be able to make a function, but I don't know how to write a test. And I don't write functions without writing a test first. So I want to know, how do I write a test? How do I write a test? We're going to take this code and put it in here. Interesting. Are we going to put it? We're going to need a main to play. Well, we could have a main. We don't have to have a main, but I would like to know if I have a print line. Hello world. Yeah, do that. Then can I put, no, not that. Did I not say copy? Copy. Paste. Okay, so I can put the functions after the main, which is nice. Why does it need to say allow dead code? What happens if I don't have that? The function bad add is never used. It's used down here. Macro expression. So assert equals is a macro with the word match. We're going to have to learn about the keyword match. I don't understand why this one is giving me a warning about not being, not being used. And we're just using this to hide that warning. And this doesn't have that warning. Now, this one, I'm guessing pub is public, and this doesn't have public. And nothing else that we ever did had public. Oh, okay. So it's not public. The reason this one it's not saying this is not used is maybe somebody somewhere else uses it because it's public. So it's not giving me that warning. This is not using it because we're not using it in our main. But if I said bad add 1,2, then I bet this dead code will go away. Yeah, okay. So the dead code was because this private method or function or Do they call them methods or functions? Function. Okay. Oh, duh, fn function. Okay. So this private function was not being used in the main, and that's why it had a warning. So even though it was being used in the tests, it wasn't being used in the only piece of code that could actually call it for real. So then we look at these tests. I guess this makes that looks, it's sort of like an annotation in Java on a module named tests. Use super. Okay, so that feels sort of like it namespace. You like use in C++, where you're saying you don't need to put in all of the path to find things that are in the superclass, and that's good because these things are there. So I have an annotation for a test. This function tests, checking to make sure that if I add 1 to 2, I get 3. And this one is checking that if I use bad add 1, 2, and I get 3, but bad add is going to fail because it's not really adding. So I guess he's trying to show us what happens when a test passes and what happens when a test fails. Can I, if I run this, it's probably going to run the main. Yeah, that ran the main. Oh, I:10. Where did the I:10 come from? Oh, when I put a variable in there. Oh, no, there's the I:10. Okay. Sorry, a little distracted there. If I get rid of this, no main. It's going to be mad at that. How do I run the tests? Test can be run with cargo test. All right, let's try that. Oh, test add passed, test bad add failed. I kind of wish there was like a pretty you know, like this works. It shows me what works and what doesn't work, but it's not really like, you know, when I use this kind of thing in IntelliJ, I can run. Oh, wait, what happens now if I do this? I wanted this piece. Okay. So I wonder, and now it has run the tests up here. So somehow when I did this, it made it realize that there were tests in there, and now I can run them the right way. And it can show you exactly where it panicked. Okay. All right. So at this point, I have figured out variables, the cool mutability versus not mutability, if statements and while and for loops. Are there while loops in Rust? Well, I don't want an infinite loop. Gross. Oh, while. Yeah, that looks like a normal while loop. For, we saw. For and iterators. Oh, we need to go learn about iterators. I guess this is a vector. Okay, so there are clearly some more complicated types than just variables. Duh, of course there would be. Oh, remember how we said this was to less than? You can put an equal sign there and make it be less than or equal. Okay, bottom line. We have variables, mutable, immutable. They don't, it will not switch types for you. So you have to be really careful about the types of your variables, which we actually like. Functions and how they return things, how we pass information into functions, and the interestingness of call by value, call by reference, call by mutable reference. No, we're not going to do if let. Okay. I think that is plenty for our first excursion into Rust, and I will come back soon with my next excursion to Rust. I really like that the tests are in the same file as the thing they're testing. That's pretty slick. Okay, for my next go around in this, I'm thinking I'm going to play with arrays, and apparently we can slice arrays, and maybe vectors and iterators, so it'll all be about combining lots of things into one data set, and how do we do that in Rust. Make sure that you check out that gentle introduction to Rust. There's a lot more really good stuff at that page. Come again.